before I forget, I'm gonna have to dash out of here at 2:15 for about 10 or 15 minutes. I'll probably be back before the period's over, but I got a meeting I can't really avoid, I gotta go downstairs. But between now and then, I'm gonna give the test back and go through them, and we may even have time to touch on the tail end of section 501. So the marks have been posted. As usual, when you get your test, check my edition, and then if anything has to be changed, let me know once you guys turn them back in. And because I gotta do comments on the report cards are coming up. I don't usually do this, but it will help me to formulate some comments for some people if I can get the multiple choice back. You know, I don't usually ask for that back, but if I have both, it allows me to do some better comments if the need arises. So when you turn your stuff back in at the end, just include the multiple choice stuff with it. These are in no particular order. Daniel and Drigger, Julian, Jose, Ryan, Julio, Claire, Christina.
Okay.
Is that basketball?
Yeah.
Leo, Beckus, Brienne,
Damn, that was so loud.
did you hear me? Brienne,
Oh, sorry.
Ariana, Annika,
I can work off.
Alexandria, Allison, Cassandra, basketball, Olivia, Samantha, Diane, Annabelle, Randall, Samantha Lowell, Lauren, Nick,
We have a mic.
okay, that's pretty much it. So, real quick, we'll do the multiple choice on the screen. I don't know, do I? Watch the multiple choice carefully, because I had to, with this silly computer program, it used to be the case that, if I use the same multiple choice for different classes, it would work for all of them, but I gotta input every one individually. So I made a mistake with the block F. I don't know if I made a mistake with yours, I don't think I did, but, if I did, I'll just do it again. But I think the ones in block G are still okay, so, but again, just watch that carefully as I go through it on the screen. Anyway, the first question read, what type of reaction typically results in the formation of a precipitate when two reacting solutions are mixed? That's double replacement, and that was B. Number 2 read, which of the following pairs of substances could represent the products of a neutralization reaction? And that's salt and water, that's D, in ACl and water. Finally. Oops. Number 3, that was a pretty easy one to balance because it was CNN H2n plus 2, but that was odd, so that 1 stayed there, so when you balance it, there was 8 in front of oxygen, pretty straightforward. Number 4, which of the following reactions will proceed? Well, copper will not replace sodium, magnesium will not replace lithium, iodine will not replace fluoride, but chlorine will replace bromine. So again, just the activity series. Number 5. Some of these didn't photograph too well. Which of the following is true for an endothermic reaction? If we go by process of elimination, potential energy of reactants exceeds that of products. No, that's exo. Energy released is greater than activation energy. No, that's exo. Sign of delta H is negative. No, exo. So it's got to be A. Reactant bonds are stronger than product bonds. And that makes sense, because if the bonds are stronger, you got to spend more to break them than you get back when the product bonds form. Number 5 was also about or 6 was also about energy. Which of the following is true for exothermic? 2 of these don't make sense. If potential energy goes up, delta H could never be negative, and if potential energy goes down, delta H could never be positive. So either it goes up and delta H is positive, which isn't true for exo, or potential energy decreases and delta H is negative, which is true. Number 7, which type of reaction produces carbon dioxide and water? Hydrocarbon combustion. It's not the only type of combustion that produces carbon dioxide and water, but that always does. A. Which of the following reaction types is usually endothermic? Decomposition. And again, that's pretty straightforward. The multiple choice overall was pretty straightforward. In a stoichiometry problem, if you're given grams of A and asked to calculate grams of D produced, well, if you're given a balanced equation already, then you're going to go from grams to moles to moles to grams. So step 1, you have to turn grams of A into moles of A. Number 10. That's a terrible photograph. In any stoichiometry problem, the first step is always to generate a balanced equation. Because without the mole ratio, you can't do stoichiometry. That's D. Consider the following balanced chemical equation. Again, you can't see that very well, but that's 4 aluminum plus 3 oxygen gives 2 aluminum oxide. How many moles of oxygen would be required to react with 12 moles of aluminum? If the ratio is 4 to 3, you need 3 moles of oxygen for every 4 of aluminum, so 3/4 of 12 is 9. Number 12, consider the following balanced equation. How many grams of water can be produced when 2 moles of sodium hydroxide react with excess carbon dioxide? Well, the mole ratio is 2 to 1. You have 2 moles of sodium hydroxide, so you're going to make 1 mole of water. 1 mole of water has a molar mass of 18 grams. In a chemical reaction, we identify the limiting reactant as the substance that is used up first. Once we use it up, we stop making products, ergo the term limiting. And then the last 2, the unbalanced equation for the reaction between zinc and hydrochloric acid is, well, it's pretty easy to balance, put a 2 there. If 36.46 grams of hydrogen chloride reacts with excess zinc, what volume of hydrogen gas measured as Tp will be produced? Well, this happens to be 1 mole of HCl, and because it's a 2 to 1 ratio, that means you're going to make half a mole of hydrogen. 22.4 divided by 2 is 11.2. The last one is limiting reactant. If 32 grams of hydrogen gas are reacted with 32 grams of oxygen gas, the actual mole ratio, moles hydrogen to moles oxygen, is, well, the required mole ratio is 2 to 1. But the actual mole ratio, that's 16 moles of hydrogen to 1 mole of oxygen. So there's the actual mole ratio, which is 8 times bigger than the required, which means actual mole ratio is greater than required, and oxygen is limited. So, any mistakes that you saw, or did I punch in the right answers? Good. So let's do the written response. Question 1 kind of combines 4.1 and 4.2 as I said it would. You had to first complete the word equation and then write a balanced quantity equation. Notice that each of those was that third category of double replacement where we have 2 reactants for 3 products. So in the first one, an acid plus a carbonate salt, if you wrote carbonic acid, that's wrong. Carbonic acid is what you write to balance it, but you don't get carbonic acid. It immediately becomes water and carbon dioxide, and you didn't have to write dihydrogen monoxide for water, just water's fine. So the products are gonna be lead 4 chromate, not lead chromate, lead 4, and water and carbon dioxide. That was worth 1. And the balanced equation was effectively worth 3. You had to get all the right formulas, and then you got a mark for balancing it. So you obviously had to know what chromic acid is, but again, ic acids come from 8 ions. So the balanced equation looks like this. Lead 4 carbonate is not 2 and 4. Okay? Always reduce. We're gonna get lead 4 chromate, and but it's in usually it's not 2 and 4, reduces to 1 and 2. And as you started with making carbonic acid, you have to replace them with the same number of carbon dioxide and water. If you wrote both, and a couple people did this, carbonic acid and in brackets water and CO2, don't make me pick. Erase one of them. Okay, so the carbonic acid was the way to balance it, but then you gotta replace that with the same number of water and carbon dioxide. B, the products are gonna be chromium 3 oxalate and ammonia and water. Again, not ammonium hydroxide. The balanced equation looks like this.
This is how they did it in the work. When it said I don't work equation, it was this long acid. I guess that makes more sense. I mean, they're both technically correct. I mean, your products aren't even right anyway, so. Biggest sell of all time. I only fucked up one question this time. I know, I didn't get this right, like at all. It's like I didn't have time to go.
So 4 for each of those, that was worth 8.
This one was like,
Number 2, I said I would give you a question from the energy section.
I didn't get this one.
Given the following delta H value, write a balanced thermochemical equation and an equation using delta H notation. You need 2 intact chemical equations. The fact that it's positive 46.1 means that it's going to be endothermic. So the thermochemical equation has to have the balanced decomposition of ammonia. And both of the elements in that binary compound are diatomic. So thermochem, because you've got to have a 2 there in the balanced equation, you got to multiply 46.1 by 2, so we have 92.6 kilojoules per mole. That's important. And then you get N2 plus 3H.
Is this not?
That's the thermochemical. Delta H, you gotta write the equation again. You can't just write the delta H value.
Oh, I didn't do the top one right.
And then you write over here, delta H equals positive 92.2 kilojoules
I
per
could have had
mole.
fun with somehow.
Or if you
This is
want
wrong.
that.
This is wrong. This is right. This is right. This is wrong. This is. I could have had full marks. I could have had full marks.
The straight stoichiometry question was number 3. One of the most efficient drying agents known is tetraphosphorus dicoxide. This compound will even remove water from pure H2SO4 according to the following balanced equation. So you actually turn the acid into a different acid. What mass of P4O10 is required to produce 1,008 liters of sulfur trioxide gas measured at STP? I'm not gonna write the whole thing out on the board, but you're gonna go from liters SO3 to moles. And notice there's 4 sig figs given in the volume, 1008 liters. But STP has 3 sig figs. So when you're done, you gotta round to 3 sig figs. So you're gonna go liters SO3 to moles SO3. The molar ratio in the balanced equation is 1 to 6. And once you get to moles P4O10, you determine the molar mass, 283.88. You do the arithmetic and round to 3 sig figs. It's 2.13 times 10 to the 3, or 2130 grams, without a decimal after the 0. All right? Number 4 was the limiting reactant question. Nitric acid can be used in the production of various high explosives. RDX, the main component of military explosive C4, is produced by reacting concentrated nitric acid with hexamine according to the following balanced equation. And just to keep them straight, I'll name them for you, and then RDX is the following. RDX stands for Research Development Explosive, sometimes called C4. Okay? From the balanced equation, and notice, for none of the stoichiometry did I expect you to balance the equation. I gave it to you. The only balancing was question number 1. So the required mole ratio, I usually put the big one on top, but you don't have to. 4 moles of nitric acid for every 1 mole of hexamine. The actual mole ratio, you're given a volume of the nitric acid, and you're given a mass of the hexamine. Notice that there's 3 sig figs in the volume and the concentration of the nitric acid. There's 4 sig figs in the hexamine, although sig figs is not that much of an issue here in this question. The actual number of moles of nitric acid you have is 6.4. The actual number of moles of hexamine you have is 1.498. That works out to more than 4 to 1. So the as actual mole ratio is greater than the required mole ratio, hexamine is limited. Now, if you did that arithmetic and then you just said hexamine is limited, but you didn't say why, you probably lost a mark. And I wrote why. Don't expect me to interpret those 2 values for you. You have to write the statement. If you chose to put hexamine on the top, then the actual mole ratio would be less than the required mole ratio. Either way, hexamine is limited. 4 marks. Now notice that the hexamine in question in 4A was given to 4 sig figs. So you're not including nitric acid in the calculation for 4B, so you gotta go with the 4 sig figs. You could have either started from scratch with the mass of hexamine and then go grams to moles to grams of RDX, or you could just take the moles that you calculated, 1.498. So 1.498 moles of hexamine, the molar ratio in the reaction is 1 to 1. Molar mass of RDX is 222.15 grams. You want 4 sig figs in this answer, 332.8. The last question was the excess, the percent yield question. And notice that because I've given you excess lead-2 nitrate, it's not included in the calculation. The first thing you have to do is get the theoretical yield. And the theoretical yield, based on the fact that you've got 3 sig figs in the volume and 3 sig figs in the concentration of arsenic acid, means that your answer should be the 3 sig figs. So the theoretical yield works out to be 695 grams, 3 sig figs. Then you have to calculate the percent yield. The percent yield is the actual yield, which you're given, divided by the theoretical yield. Now, I would accept either 85.0 or 84.9. If you use the 695 grams as your answer to A, if you divided that into the actual yield, then your answer really should have 3 sig figs. Okay? If you use 694.6, knowing you have to end up with 3 sig figs, then you probably got 85%, but either one works. And I think for the most part, most people did pretty good on number 5. The fact that there are opportunities for part marks, and you probably see a lot of halves on your test, depending on who you are, be rigorous in checking my addition, because I made a bunch of mistakes.
He's showing.
Probably because I was watching the hockey game early in the morning, with my addition. So once you check my addition, if there's something wrong with it, or if there's anything else you need, tell me now, because again, our report card marks are due on Monday. So if you've got an issue, come up and let me know. And again, for the report cards, could you please slide in your multiple choice answer sheet as well?
Just because I can't read. I still don't know how I'm getting this wrong, bro.
Whether I made a mistake or not, I need both.
Mr. Charles?
Yeah.
Two easiest questions. They're not even like difficult.
So were you off by 2?
Off by 4. I got 4 questions wrong. 2 questions I understand why I got wrong, because like that's just me being stupid. That one,
Small goof.
this one I didn't know. I guess this one, I thought that was the right answer, but that actually doesn't make sense. That just didn't read. This didn't read. I could have got 42. I could have.
Bro, it's show. It's show.
Could have gotten another 95, bro. Could have gone up 2% instead of 1.
This has been perplexing me all lunch.
So do you use that, or do you use
Because this is supposed to be 75 something. It's supposed to be 24 something.
It actually pisses me off, bro.
rather than
I'm genuinely mad about this.
You're up, bro. It's okay. Are you this?
I'm at an A now. Like a flat A.
Oh, like 86? I'm at 6.7. No, literally, I saw my grade. It went down 1%. I was like, ooh. Because I was at 68, and I was like, I went from 66 to 68. And I was like, man. And then I saw it went down. Excitement.
It's okay, the lab will probably bring us back up.
Well, at least show me one extra 6 thing.
Yeah, don't jinx it, bro.
That's exactly what the number was.
That actually
I just went with that and that. 332.9.
Could have got another 95.
It's okay, boy.
Right, but that doesn't. So that's
Next time I'll write down, like,
just make it clear what actual number.
He might be stressed.
What's going on, bro?
But he's a little bit stressed out.
My arm is tweaking. You see that?
Yeah.
And that's even better.
Hey.
thank you.
Yo, that's so weird. Oh, you.
Thank you.
Thank you, Daniel. Yeah.
This one, I wrote
I'm gonna die. Two easiest questions on this gas test. A kindergartner could do this.
Damn, I'm dumber than a kindergartner.
Hey, no, you got this question right.
Which one?
The products represent products of neutralization. You got that one right. I saw.
Oh yeah. Oh, is that the multiple choice? Yeah.
This one you didn't get right, but like.
I don't know. I did this.
I studied this too.
I did this straight stoichiometry really
I
good
studied this.
though. I got a 4
I
on
actually
all
took
this
time to look at this, and I still got it wrong. Cause I can't read.
It happens, man. You'll get it next test, man.
Now, did you
Fucking illiterate, bro. I'm actually illiterate.
did all this? You didn't,
God, I'm retarded.
You didn't take.
You know what? I gotta keep my 90 streak now.
You didn't use that.
Gran, the 2 easiest questions on this whole test, I got them wrong.
But you didn't start with that.
The thermochemical one with the delta H, and then products of neutralization.
Then it would be, I just had this conversation.
I thought it said
Instead
reactants.
of 1.498, it would be 1.47.
I can't read.
976. And because that
I
was
can't
less,
read.
that's
No,
why
there was
this
NaOH, and then the other.
Yeah, it's just that,
You know what? Shush.
so that should be.
I know his voice, there was no because I thought that too. It's so crazy. It's like, why are there no reactants? Oh, it's products.
I didn't make that connection.
So rad.
Yeah.
Easiest fucking question ever, bro. Fuck me. Fuck me, bro.
I don't know how I got this wrong, man.
Try and teach it to me. Maybe I'll figure it out.
I don't know.
Because I haven't looked at it yet.
You still only got a month off.
Like, okay,
So there's nothing wrong with that.
this is like the atomic
Yeah,
mass
that didn't
unit,
cost
right?
me.
And you want to find the percent abundance
Number
of this
6?
thing, right?
Uh huh.
So it's
I still got about 10 minutes.
X is like one of these.
Yeah.
I don't know what that means. And then the other one
Let's
has to be 1 minus X. You gotta look
Quickly
for X.
transition
Wait, it's on my paper. Hang on.
to the last page
I just couldn't get it right, bro.
in section 5.1,
Like off by
Or the
like
second
20
last
whole
page.
numbers.
which is a diagram of the mass spectrometer. So we kind of rushed through this near the end of the last class, and I gotta rush through it again. The mass spectrometer allows us to determine for any naturally occurring sample of an element how many isotopes there are, what their relative mass is, and what their relative abundance is. And it works kind of on the same principle that Thomson employed to discover the electron, namely the deflection that a charged particle experiences in either a magnetic or an electric field is based on the charge to mass ratio. So we went through this briefly, but just to go through it again. The sample that enters a mass spectrometer has to be vaporized. So if it's a solid or a liquid, we've got to vaporize it first. Obviously, in this example, neon gas is already a gas. So the neon atoms enter the mass spectrometer as neutral atoms. Without a charge, they're not going to get deflected at all in this electromagnetic field. So we got to bombard them with electrons. And you can't really see it in the diagram, but basically this is an electron gun. We're shooting electrons at these neon atoms as they enter through this little hole. Now it says here accelerator plates. That's positive and that's negative, but when the neon atoms comes in, then they have no charge. But as soon as they get bombarded with electrons, the energy of the electron beam we adjust so that we ionize the neon atoms. And there's a certain amount of energy necessary for that. But as soon as that happens, we now have neon ions. Now they have a charge. So now they're repelled from this plate, accelerated towards this plate, and they're focused into the magnetic field, the electromagnetic field that is now in the mass spectrometer. And they're going to get deflected based on this. The bigger that is, the more their direction is changed. So as it turns out, there's 3 different isotopes of neon. All of them have a 1+ charge because we ionize them. They're all neon, so they all have the same number of protons. So for all of them, the charge is the same, but what's different is the mass. Neon 20 is the most common isotope, but then we have neon 21 and neon 22. All of them have the same charge, but they have a different mass. The biggest mass is gonna mean the charge to mass ratio is the smallest. So the heaviest one, which is this one, gets bent the least. So that's the one that's right there, okay? That's the neon 22 with the 1 plus charge. The lightest of the three, this one, is gonna get bent the most. So that's neon 20. And then there's a tiny amount of neon that's neon 21. So 20, 21, 22. Not only will the mass spectrometer tell us that those three exist, but it'll also tell us the relative amounts of each. The old version of this was called a mass spectrograph, where the detecting surface was just a photographic film. And the amount of exposure on that film then allowed scientists to calculate the relative abundance. But sometimes the film wasn't sensitive enough to detect tiny amounts of really uncommon isotopes. So if you look here, you'll notice that neon 21, only 0.27% of all the neon is that. So in a mass spectrograph, it wasn't uncommon to actually miss this. You didn't even see the impression it made. But with a mass spectrometer, you don't have that problem. So if that data is used, this represents the first type of calculation that you guys might be expected to pull off. Use mass spectrometry data below to calculate the atomic mass of neon. Well, that means what's on the periodic table? The mass value in the periodic table is, as I indicate in the what to think about part, the weighted average of the masses of each isotope. Weighted means how much of them are there. So, to get that off the mass spectrometer, 90.48% of all the neon that's there is neon 20 with 10 neutrons. Now that's the mass relative to, carbon 12 being exactly 12. We multiply that, those atomic mass units, by that percentage. Then we add to that mass multiplied by that percentage, and add to that this multiplied by this. And that arithmetic is shown down here. Mass of neon 20 times its percent abundance, and you could write 90.48 divided by 100, or just 0.9048, doesn't matter. Then add to that product, that one, and notice it's not 0.27, it's 0.27%, which is 0.0027. And then add to that 0.0925 or 9.25 divided by 100. And then when you get your answer, that's what should appear in the periodic table. But there's no atom of neon with that mass. That's just the weighted averages of the naturally occurring isotopes. Now that's one type of question that you could get asked based on spectrometry data. The other one is the second sample problem. This type of problem could only be asked for elements existing as two isotopes, meaning whatever isn't one is the other. So in this type of question, you're given the mass value in the periodic table, and you're given the masses of the two isotopes. You have to calculate the percent abundance. So if you look at the equation on the bottom of the previous page, we know what all the arithmetic has to add to, and we know the mass of each isotope. But because there's only two isotopes, whatever isn't one has to be the other. So, expressed as percentages, whatever is 1%, the other one has to be 100 minus that percent, right? Because I got to add to 100. Or if you do fractions, whatever is 1, the other has to be 1 minus that, because they have to add to 1. And that's the logic we apply to do some simple algebra. So let X equal the fractional abundance that boron 10 is. And what isn't boron 10 is boron 11, which would have to mean that 1 minus X is the fractional abundant that is boron 11. Because x plus 1 minus x is 1. They have to add to 1. And there's only one unknown. And because of that, it's pretty easy to solve. I couldn't give you a question like this where there were like 3 or 4 isotopes. That wouldn't be solvable. But for this one, it is. So there's the arithmetic. There's the fractional abundance that boron 10 is. Multiply that by the mass of boron plus the fractional abundance that's boron 11, which has to be 1 minus x. And I picked boron because the numbers work out real evenly. X ends up being 0.2000, which has to mean the fractional abundance that's boron 11 is 0.8000. And if you turn it into a percentage, that's 20 and 80. And if you look at the actual mass, it kind of makes sense that there's more boron 11 than boron 10, because this number is way closer to 11 than it is to 10. Now, if you look in the practice problems, I've got to go in like a minute. The first practice problem is the first type of sample problem. The third practice problem is the second type of sample problem, where there's 2 of them there. If you look at the review questions, number 8 is a question like this for the calculating atomic mass of magnesium. But number 10 is a question like this, where silver also exists as 2 isotopes. Now I got it dashed downstairs. I will be right back. I know this is exciting, but try either 1 and 3 or 8 and 10. Because on the chapter 5 test, there will be a question on one of those. Either the first type or the second type. Not both, but for sure one of them, okay? And I'll be right back.
I'm still not getting that pitch right, bro. I don't know what to tell you, bro.